Okay, hi. Thank you so much for being here, or actually allowing me to be here. I think that's the thing to say, because clearly, as you can tell, I'm obviously a programmer, I'm wearing a t-shirt, but I'm not a Scala programmer. So hopefully more of you will talk to me as a result, actually, because it's good to actually share our ideas across whichever world we're from. You're obviously from the Scala world, and I'm from the general programming world, actually, I would say. And you'll start to understand what I'm talking about, and I am going to show a lot of Ruby code, actually, if that's okay. It looks quite like Scala, so don't worry too much. You don't have to put the semicolons on the end, so that's a definite bonus. But before we even start talking about programming in general, I want to show you this picture of performances, music performances, because this is the context of my talk. And I mean, I can approach what I'm about to say in many different ways, but I think one of the interesting ways to talk about it is to start here. And to say, because I go into schools, actually, and pretty much a very similar talk I'm going to give to you, I'll give to school children aged 10 plus. And I'll say to the school children, what's this a picture of? And they're like, oh, that's someone performing. I'm like, yep, and that's me performing. And that's great. But what's more interesting, I think, is that's me programming. You see, when I make music, I write code. And here is an example of me writing code. Now, why on earth would you want to be on there writing code, right? And I think this is a really interesting opportunity to talk about what programming is in general. Because I think today, in our day and age, programming is still very much in its nascent, very, 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 very early days. And we can all be very excited about how detailed and advanced and sophisticated we've got an idea what programming is. But how old is programming compared to maths? You know, how old is it compared to science in general? How old is it compared to philosophy? How old is it compared to music? You know, and we can even look at the history of humankind, and there's extremely strong evidence to suggest that as humans, we were making music before we were talking. And so I think it's really important to put these in perspective. And so here, making music is a very human social act. And what I'm doing is sharing my ideas of music from my mind out to the people. But when I go and see other people perform like this, making typically electronic music, it's very opaque. I've got no idea what they're doing. Like, what am I doing on that stage, right? Clearly I've got some kind of laptop, so, I mean, I'm possibly using that. I might have pressed play on iTunes or something, although that doesn't exist anymore, but I could be pressing play on something, or I could be doing some slight tweaking, or I could be making it all live and improvise, which is exactly what I'm doing. Now, when you're using opaque techniques, that a lot of current contemporary electronic musicians do, that's pretty much all you'll get in terms of understanding their process. So if, obviously, you're loving the music I'm making here, right? It's amazing, isn't it? If you're liking that music and you want to go home and do something similar, how do you even start? Like, what do you duplicate? Where's the open door to show you how to do something similar? Right? There isn't any. And as programmers, we really understand how the benefits of sharing our work with each other. The ability to actually go and see not just what the current state of play is by sharing the source code, but also sharing the entire history of that source code so we can see the story of how you got from A to B. And that's incredibly useful for understanding and sharing our knowledge, not just of our projects, but how to make similar projects or how to make things that other people haven't even dreamed of yet. And so when I'm performing, clearly as a programmer, I'm doing exactly that. I'm projecting the code to the audience, so the audience can see what I'm doing. In this case, the code is merged with some visuals of me moving and typing, but here's a much more clearer example of that code. And that code there, which the audience is able to see, is exactly the code which is being evaluated live and generating the audio that the audience is dancing to. So here is an opportunity to get inside the musical process and start sharing it, start understanding it. Now, hopefully you can understand now that the language I'm using is pretty much irrelevant. Whether it's Scala or Ruby, whether it's Clojure, whether it's PHP, it doesn't really matter. What matters is that the process is visible and the audience, if they want to, can get inside of it. At that point, we can start to debate what language might be a better dialect for describing our musical processes. But really, the language isn't really important. The important point is they're actually starting to open up the box, the sort of closed box of music, and make it visible. Now, what I find interesting about this is exactly the same system I used to perform with. I also go into schools and teach programming with. So there's over 1.5 million people who've used this software, both to teach code, as a first experience with programming, and to get started. And it's really to be a very exciting thing to try and think about how we can try and open up the clear joy and passion and excitement we have, all of us, I'm sure, about programming. But then when I'm going to go to conferences and talk to people, my standard joke is, it's not really a joke, it's kind of depressing, isn't it? I mean, I've got 3 kids now, so I never really get invited to parties. But so if any of you have parties, please invite me. But if you ever go to parties, how many of you are honest when people ask you, what is your job? Right? Because when you say I'm a programmer, it totally kills the conversation, doesn't it? Like, how do you move on from there? People are like, oh, okay. That's it, gone. Right, so now I lie, I say, I'm not a programmer, I'm a musician. Oh, cool, what do you play? Guitar? What, saxophone? No, I play code. And now I've got them, right? We've got a conversation started. And I think, it's a tragic thing. I think this is a really important thing for society, is that we still yet to understand what programming is, by and large. We do, to a certain extent, but society in general has no idea what programming is. And this is why it's very hard to talk about it at parties. And so here, I'm actually programming at the party. You can actually become the party as a programmer if you're coding the music. And that allows you to start that conversation about what programming is. And this is the critical thing. So how many of you think that written language is important? Right? Obviously, all of us. And obviously, there's a point when humans didn't write language. And now the majority of us do, and certainly in the Western world, we all learn, or we all are suggested that we should learn how to read and write. Now imagine, just a thought experiment, if the only output, the only purpose for reading and writing was to write legal documents. Would that be a world you want to live in? Now imagine if the only output for programming, the primary output for programming is business. Would that be a world you want to live in? Because it's the world you live in right now. How many of you are programmers? How many of you work for business? There we go. How tragic is that? Seriously, it's utterly tragic, right? Surely we should get more programmers doing more things than business. It's not like that we shouldn't be doing programming for business. That's clearly a very important thing. Right? We are able to really do new things and push our financial worlds and our buying and selling and how we do all our corporate stuff. We can do that much more effectively when we program. There's lots of opportunities to innovate and disrupt and all that kind of cool stuff. But surely that's not the end. The end game of programming is just to do business stuff. Well, maybe I'm talking to the wrong audience. I hope I'm not. And so here, we are able to start that conversation, or not necessarily start it, but advance it, or to try and facilitate and to actually show that programming is much, much broader than business. Just like reading and writing is much more broader than writing legal documents. Right? We write poems, we write letters, we write to-do lists, we text each other stupid jokes. Right? What are the equivalent of those things for programming? And if we're going to get more people programming, and I believe that's really important, I don't think we should get more people programming because there's more jobs. Like, we don't teach sports at school to make more sports people, do we? We don't teach history at school to make more historians. Like, we do sports because it's good for our bodies, it's good for our mental well-being. We teach history because it's really important to understand the histories of the world. And those who don't are there to repeat the failures of the past, which is exactly what's happening right now. So, seriously, right? It's tragic. So I am European. I'm not English, by the way. So, there's no joke. So back to this. So this is me programming. Now, I'm going to spend a little time talking about how this works and what goes into it. But really, at any point, I can't see any of you, so I'm assuming there are some people I can hear some laughter occasionally, so that's a good sign. If you've got any questions, don't leave them to the end. Throw them at me right now, right? Because it's really important that I make sure this is interesting for you and not just interesting for me just to give a monologue. So that's the background. I go into schools, I teach this stuff, I perform with it, and it'd be interesting to show you sort of how it works a little bit. I think it's quite interesting technically. So here's the software. It's called Sonic Pi. It's entirely free. It's open source. In fact, actually, I can probably easier to show you the website. So you go to this website and you can download it. And it runs on Mac, it runs on Windows, even runs on the Raspberry Pi computer. Actually, it was designed initially to run on that thing, but it's since evolved much further since. And once you download, open it, you get a text editor where you can write some code. There we go, beautiful code. Now, is that going to compile? Well, it doesn't matter. We don't have a compiler. We're going to interpret it live. It's going to obviously run and make an error. And this, when I go to schools, this is really important, actually. People don't realize that programmers are always in a state of error, right? It's normal, right? It's normal when a compiler doesn't compile. It's normal when you get an error, a runtime error like this. Because when you've got things working, when the types are compiling, when the errors, tests are all passing, then you're on to the next problem, right? It's not working again. And I think people have this weird perception that programmers are in this state of perfection at all times, right? So it's clearly important to say, actually, errors are a normal state. And then it's also useful to talk about code as magical spells. And in this case, you need to know the magical vocabulary of your magical spells. And in this Sonic Pi program, this is the simplest program you can run. And we can run this code and it can make a beep. Great. Now, this is super exciting. Because when I go into schools, and well, when I first went into school about 7 years ago, and I had this challenge of trying to teach kids how to code, I had no idea how to start, And then we had a new curriculum in the UK that came out that talks about sorting algorithms. How many of you have fun with sorting algorithms? Probably most of you. But are we trying to get more people like us programming? No, we're not. We already have enough of us. We need more people of different kinds, right? And so the things which excite us are probably not the things we should start teaching. And so sorting algorithms, I don't think, are widely accepted as exciting, right? Just a thought there. And so the other thing is, like, when you go into school, I don't know how many of you been to, how many of you have been to school recently? Right, there's a challenge. All of you should really strongly consider, if you have any spare time, going into your local school and helping out a little bit. Starting up a club in the evenings, the afternoons, talking to the computer science teacher, helping them, because they drastically need your help. Absolutely. And when you go in, you'll be surprised by how little time the teacher has relative to how much time they have to spend organising and coordinating and controlling, right? They're telling everyone just to be quiet. So when you've got them quiet, what are your 2 sentences for getting kids excited about programming? Is it open up IntelliJ? Yeah, no. Emacs in my case, no, not going to work. Right, so this was a challenge for me. It's like, what would that starting point be? So this is my starting point. So everyone can write the word play, everyone can think of a number, and everyone can press a button to press run, and you can hear that sound. And you've already got this opportunity to talk about numbers and abstraction. Numbers can go up and go down, and as programmers, we'll always look for things which map onto these mathematical models of abstraction. So in this case, what else can go up and can go down? Pitch. So higher notes, higher, lower notes, higher. And we're in a cinema, so let's... Oh, no, we haven't got much. Let's go for that. Let's go for this. Oh, right, okay. The cinema needs... This is not a good cinema for Star Wars. I ran this particular program in a cinema in the Netherlands, in Ada, and the bass just shook. There was a ton of Java programmers, and they were scared witless. But also in schools, right, this program's not going to work because they have no bass. So you definitely need bass for this kind of thing. So, but obviously, we could start talking about the range of human hearing, right, too low, too high, right, so we can talk, that's really interesting. And 100 is probably the highest. I'm not going to do that because it's going to be horrible to hear. A fun game to play with your friends and family is to get everyone around at Christmas, crack open Sonic Pi, and keep going higher until someone in the room can't hear. It's typically the elder people, right? And then just keep going higher. So about 100 everyone can hear. Slightly higher, it starts to become something that only the dogs can hear, certainly the children. That's a lot of fun. Now, once we've got pitch, right, the next thing to think about is, well, at the moment, we've just got the ability to make a note, but let's see if we can make a melody. So I'm going to play note 60, then note 75, say, right? So the way to learn Sonic Pi, because we're actually working with a language which has temporal semantics, has a semantics that is probably quite different from any program language you've ever used. So the first thing is to think about what that might sound like, imagine it in your heads, and then we run the code. And that's probably not what you imagine. Or imagine note 60 and then note 75, right? We do here have a language which is imperative. It is running line 1, line 2. But this, in a teaching context, is an opportunity for learning. Everything's always an opportunity for learning. And we can talk here about how fast the computer is. Does line 1, then line 2 so quickly after another, you can't hear the difference. At least that's how it used to run when I first implemented it. Recently, I made this so it's what we call audio rates timing. So it's 1 over 44,100th of a second difference between the two sounds. So they are pretty much sample accurately played at the same time. This is a really important, time is a really important thing for music. And in this program so far, we haven't talked about time. So everything is simultaneous, right? So if I write another note here, let's say 67, you can see at the right-hand side, we're actually playing at time 0, all the notes at the same time. We don't talk about time yet. So we need to talk about time. So let's sleep the computer. Now we have, lovely, the ability to make any melody you've ever heard in your entire life with 2 commands. And children do. Now this is important to realise, right? So once you've given them these 2 commands, they literally can make any Daft Punk, any Tchaikovsky, any Radiohead, right? Because Western music is typically 2 things on its base level. Obviously there's a lot more stuff. There's a lot more feeling and nuance and timbre, whatever that means. All these beautiful things. But in its essence, Western music is which note to play and when to play it. And we have those 2 parameters there in our language. And these things are very, very accurate and very, very well timed. So children can really make, and obviously we're not limited to the integers. We can use floats here. Also this kind of stuff. So we're working with microtones, so we can do very interesting things very quickly. Now, obviously, it's important to point out that, I don't know how long have I even started, okay, good, I've got lots of time. When I'm doing this, right, I'm not running this program, right? So the question now is, how long have we got to explain how I get from there to hit something interesting that people can dance to? And I'll be doing a demonstration of this, actual performance, tomorrow on the boat. So I really want you to come along and have a listen and maybe a dance and see what's going on and ask some questions. So we'll get to where this is. But what we're doing here is demonstrating how to get started and the temporal semantic of what's going on. Now, if you're interested in what this means and how this operates, and it's also important to point out that there aren't any types in sense of static typing. I know that's necessarily a bad thing. But in the absence of static types, I do have formal proofs. So this is when I was working at the University of Cambridge, when I first implemented the system. I wrote a paper with my friend Dominic and my supervisor Alan, and we took the ideas of Sonic Pi and we wrote them I wrote how it works in a very sort of engineering sense. I'll explain this in a moment. And then Dominic took this and wrote a Haskell implementation of it, and then also went down and wrote some formal proofs of it. So we can demonstrate that timing is sound, and that's a really important thing to do. But it's actually useful to look at why this is interesting, because when I run, say, this program, let's think about this. Play 61, say. Line 1 does actually take some delta time to execute, and line 2 takes some other delta time, and those deltas are not the same, depending on what the computer's doing, whether there's other programs running, whether the scheduler kicks in, the operating system kernel kicks in, does stuff, some I/O happens, some disk reading happens, and so. In the early days, when I was running this on a Raspberry Pi, which was especially the first one, which was an incredibly slow machine, you would get drift, so the timing wouldn't be accurate. Now, this wouldn't be enough to be able to hear, but in a moment we'll show very quickly that we get into a multi-threaded situation very quickly. And when you have 2 threads which are running, and they have these different deltas, those threads, one might be making a rhythm, one might be making a melody, they get out of time pretty quickly. And so it's important to also to ensure that you account for those delta times. And you can see here, actually, a diagram of these things adding up very, very quickly. And so the actual real wall clock time after the play D at the end is all those deltas added up. And each of those deltas is important to realise is that they're non-deterministic. You've got no idea what they're going to be, right? So this is where the drift comes into play. So we can see, actually, what happens in the system is that we account for that. We actually we run everything ahead of time. So we schedule everything ahead of time, and then when we sleep for 1, we actually sleep for 1 minus the time it took the computer to get to that point in time. And so we're always accounting. Oh, that's very quick. We did a pop filter, accounting for that drift, and then making sure that as long as the drift isn't larger than the schedule ahead time, and if that doesn't mean anything to you, please do read this paper. Then we're all good. But it's always going to make sure it's in time. And what actually happens is that this is a asynchronous system. So this language, which is, well, the GUI is a C++ program, which is just a basic editor. When I press the run button, it takes the code, sends it over the network to a server running, which is a bit like Nginx, but for music. That interprets this code, and the results of that are side effects. And those side effects are more messages to another server, which is called SuperCloud, which is an amazing sound synthesis engine, which then interprets those commands and turns them into sounds. And those commands it interprets have timestamps, so you're able to timestamp those. So although we haven't got explicit timestamping here, all that's happening behind the scenes. Now, saying all that very quickly, because I don't want to go into too much detail right now, I will later if you're interested, but what's important to me is that when you have sophisticated systems, and I'm going to argue this is pretty sophisticated, it's really important, or can be really important, to make the interface, the language design, the API, very simple. In this case, everything in this system is simple enough for a 10-year-old child. Every part. And we're going to do concurrent programming in a moment. We've got deterministic randomization. We've got live coding. All of that is simple enough for a 10-year-old child. We've even got time warp state system and go back and forward in time and a tuple space that is thread safe because it uses time as its main mechanism of sorting, of total ordering. What's important to realize here is that all this stuff is, the kids don't need to care about all that stuff, about asynchronous programming and servers and all that time-stamping stuff. It's all simple. Now, I had to do that because it was invented for working with schools, with children. And I thought this was going to be a really simple toy that had no value whatsoever beyond just fun, right? And at the time, I was working on this other thing called Overtone, which was exactly the same idea implemented in Clojure. And I was doing crazy stuff, performing with Emacs and random GSL shaders and all sorts of nonsense. And it was a lot of fun for me, but nobody really, not many people, some people could, but most people couldn't really do the same kind of thing. Because it's not that they couldn't, but the barrier to entry was nuts. Right? You had to learn Clojure, for example, to start off with. You had to learn about synthesis design. There was no sounds to play. You had to design your own sounds. There was no timing mechanism. You had to make your own timing mechanism. Right? There was no concurrency system for doing two multi-threaded band members at the same time. You had to design your own and implement them. So although it was all technically possible, the amount of effort it was to even get started to an interesting place was so much that really was it was a barrier. I mean, I gave a talk at one of the Clojure conferences and walked around the corridors of the hotel afterwards. It was lovely to hear people going from bedrooms, right, with people like doing crazy sounds. But no one got further from that, right? And so that was, for me, it was depressing to see that, although the system was interesting to me, others couldn't really share in that joy easily, right? And so what I learned from working on this system was that it's not, well, at least for me, I mean, you might not agree with this, but at least for me, it's not just good enough to do something interesting. You want to also make it easier for people to follow you, right? So it's like kind of hacking your way through the jungle to look for the exciting treasure, like golden pyramids or whatever, and then making sure you lay a brick road behind you so others can follow if you got to an interesting place. So this wasn't doing that laying the road. This was just doing the foraging and finding interesting places. And Sonic Pi was really the road that other people can follow. And that's why there's a few thousand people have used Overtone and more than 1.5 million people have used this system. And I think that's really important. And when you're working on your systems, you should be also thinking, I think, about how your APIs and your languages and your designs are simple. Because the other benefit was, whilst I was making this simple for education, because that was the goal of this, it turned out that it was more fun, more powerful in terms of expression than Overtone, because everything I could do, I mean, I could do more with Overtone. Like in terms of, like, imagine it as a vehicle, you can traverse more kinds of lands with Overtone. You could take your musical things into more interesting spaces, but it took more time. And this is another thing we don't talk about when we talk about programming. We've got time in terms of when to do stuff, but we've also got time in terms of how long it takes to do it. Right, there's lots of different definitions of time. And so you might come along to me and say, Sam, this Haskell proof is beautiful. There's no way you can replicate that in Ruby, whatever. Right? Fine. I might then say to you, how long did it take you to come up with that proof? Right? If it took you 5 weeks, it might have done, easily. Right? And you had a year for your project, or that was part of a year's worth of thing, that's fine. Right? Whereas when I am doing this, I don't have 5 weeks to write my thing. I don't have 5 minutes, actually. I don't have 30 seconds. I have maybe 10 seconds. So what are the kind of programs you could write in 10 seconds? Is an interesting thought experiment. No joke, right? Because when we start to push programming into other spaces, we have other constraints. And in my case, when making music, timing of how long it takes me to think of an idea and implement it, and to debug problems when they've gone wrong, that's utterly critical. When things go wrong, as they do all the time, I need to be able to fix them in 5 seconds, 10 seconds, right? So that's also a really interesting constraint. I can't just stare at a log trace and really think about, I haven't got that time because the audience will all left. Right? There was a point actually when my early system Overtone where it took me 20 minutes after my start time to actually get everything working, right? And the vendor person who came along, she said, Sam, you've got to actually get off the stage now, it's not going to work. And luckily at that moment I got it to work. But that would have meant my gig would have gone, right? And that was just 20 minutes. Right? So you've got to really think about these kinds of constraints. And when we're pushing programming into new spaces, we come along with new kinds of constraints. So there we go. Timing's a really important thing. Making sure it all works correctly is really important. I've thought about this very deeply. This paper, Temporal Semantics for Live Coding Language, is something interesting to read potentially for you to see how this works under the hood. And this system is able to do that. Now, what else can we do with it? How do we make it interesting? So when you go into schools, we teach the basic curriculum stuff, which is it's just like this kind of like do more line 1 than line 2, line 3, boring stuff, conditional stuff, functions, well, not even real functions, methods really. Not that exciting, but we can do all those kinds of things. What I found interesting it wasn't how to scaffold this kind of stuff onto the computer science curriculum in the UK, because that was pretty tedious, to be honest. What was much more interesting was how to engage the children. How do you keep them interested, right? Because that could actually keep you interested for a little bit, but that could keep like a 10-year-old interested for a while, and actually they do write lines and lines and lines and lines of code just doing beeps. But then you're working with our elder kids, like 13, 14, they're going to get bored pretty quick, because they're like, oh, that's not like the music I listen to. Oh, okay, well, what is the music you listen to? And they say they'll talk about drum breaks and rhythms and hip-hop. And so it's important to break out from the basic sine wave, which is what this is, into more interesting sounds. So you can pop out into different synthesizers. So here I can play, well, actually, if I play E1, so you can also play cymbals, if that means anything to you musically. And you can also change how long notes last for. That's E1 for 8 seconds. And you can notice that's note 28 if you want to work with the numbers. And typically in classes I'll stick with the numbers because using note names like this is a barrier to entry. If kids think that you need to know what E flat minor sharp to the 10th minor pentatonic whatever means, that's a huge barrier to entry to most people. So sticking with numbers matters. But we can also change the synthesizer. So just if I like to buy a keyboard, I might change the voice from piano to guitar, whatever. So let's try the Prophet synth. Make it a bit louder. But we can also change interesting things like this cutoff value. This is nice. Now, this is interesting for two reasons. One is I can really have a really dramatic impact on the timbre, the sound of the sound. But the more astute amongst you will have noticed that those sounds, they overlapped. Right? They didn't wait for the previous sound to finish before the new sound started. So I already have a concurrent system. Every time that goes pink, I create a new thread, and the code in that screen is executed within the context of that thread. And the previous threads are still running. It doesn't wait for them to stop. And I have semantics to allow me to do that waiting if I need to, but by default, the sounds just overlap on top of each other, which is a really nice. So I now can do drone music super easy, right? So I just make this release 8,000 million seconds. It's going to go on forever, and I can add more sounds. So I can get this going. Like maybe like. People listen to that stuff for hours. And so if you want to do that, that's just a couple of lines of code, right? So you can just layer them. You can change the pitches by small. So what does it mean to add 0.4 to the symbol E1? Well, it doesn't mean much as a programmer, but in the context of music, it's fairly simple. That I'm adding 0.4 of a MIDI note to a well-defined note. And so this is a lot of fun to play with. So that one thing is to be able to change the timbre, which you can do. The next thing is to actually work with pre-recorded sounds. So here is the loop amen break. Right? Now you all probably recognise this drum break. It's very, very famous. One of the first uses was when it was played at half speed by Dr. Dre. So this sample was used in Straight Outta Compton. He was rapping on top of here. Now, what I find most amusing, it's probably not the sense for you, is when I go to schools, kids know Dr. Dre for the headphones. What is that about? So, I don't remember him for the headphones at all. So you got that. You got obviously this kind of Bristol sound. A bit later you got in London. Bit of that going on. So by changing the rate of a sample, you can really modify its sound dramatically. Now, what was really interesting to me was that jungle music, for example, took this breaks like this and sliced them up using sort of electronic scissors, a bit like you can get a newspaper and chop out all the letters and rearrange the words into a new poem or letter that didn't have the same meaning as the original piece. You can do the same kind of thing with music. But it was a very painstaking, slow process. So my thinking was, how do I do something like that that is simple enough for a 10-year-old child? And so the first thing to think about was to imagine listening to all the different drums, right? So you can hear that as a sequence of drums, right? So you can imagine that as a list or a vector or an array or whatever you're going to use as a data structure to represent individual drum hits in order, right? So it'd be cool if we could, and these in music, or at least in sound theory, we can look at that in terms of energy, where the sound goes from no energy to lots of energy. That's likely to be when the drum is being hit, right? And when it goes back to zero energy, that's when they release when it's finished. So we can use these onset ideas to work through the sample. So this is an opaque sort of binary file representing where the speaker needs to be modulated through time. You can use feature detection on that to then convert it to a sequence of timings and then index through that using this mechanism here. So then now we can work through those drums as if it was an array, which it isn't, but it is, right? And so now we need one more construct. That's a loop. Do you know what a loop is? Yeah, good. Right, so we can sleep for a short amount of time, and then we can then play that one lots of times, or this one lots of times. Or, where it gets really interesting, use randomization. Right, we're getting somewhere interesting, right? So now this is how I would teach loops, which is pretty fun. Now, at this point, kids are going, that's wicked, love that. I want to get some bass, right? So you say, okay, let's do some bass. So let's comment this out. Let's make another loop, and we're going to do, let's do another sample. Or we can actually, let's use the square wave. Synth square, note E1, and release 0.5, and sleep for half a beat. That's this. Let's make it cut off 120. Yeah. So that's something like that going, and make it a bit louder. Amplitude 3. Right, so let's get that playing at the same time as a loop. Right, now hopefully you can all see what's going to come next. That's a test. This is my exam, so my interview test for you. I don't really believe in them at all, but if I was going to do one, this would be it. What is this going to sound like? Because this is what pretty much all children I've ever worked with, within 3 hours, when you've taught them a loop, want to do this. Right? They want to play one loop doing drums with one loop doing bass, or one loop doing a melody with another loop doing the bass, or two loops doing drums different kinds of times. So they run this code, and like, well, where's my drums? You know? You're like, well, that's the problem, isn't it? Because you've got an infinite loop there, and the code ever stays between lines 3 and 6, never gets to line 7, right? So you're screwed. Go, oh, well, that's rubbish. And so you go to the teacher, you say to the teacher, can we teach them threads? Because the kids want to play the drums at the same time as the bass. You know, and the teacher said, oh, that sounds great, yeah. Is it on the curriculum? Oh, no, it's not, no. So you go back to the child, and you say to the child, I'm really sorry, but you've got to wait till you're 18. Yeah? Because we'll teach you at university if you're still interested. Right? And this is tragic because at that point, you've got to the point where, and it is quite funny, but it also is deeply, deeply tragic. Because, I don't know, when some of you go into the schools and work with the children there, in your local schools, you'll see that it's damned hard to get kids to even focus on anything. Right? And when they're focusing on programming, that's a beautiful thing. And you've got them, they're working with the code, doing interesting things, and here they've actually not only taken the ideas you've shown them how to do a loop, but they've had their own idea, their own unique idea. Wouldn't it be cool to play two loops at the same time? And they've had this idea on their own, and they've tried it on their own, and it doesn't work. And they're like, oh, why doesn't it work? They're asking for help. So if at this point you say no, It's taking that beautiful seed which has just sprouted and crushing it. And they'll look out the window, they'll get their phones out if they're allowed them, they'll be disinterested and they'll be annoyed. Right? And this is, to me, a tragedy. And so in our schools, when we focus on the curricula on things which can be assessed and examined, and we have very strict understanding. I gave a talk about this to a load of teachers a couple of months ago, and one of the teachers said, "That's all great, I love this idea of coding music, but in my school, we all have to do a quiz." Like, what do you mean you're going to do? Well, that's what we examined. That's what the examiners are looking at, just quizzes. Oh, I can't help you there. All you can do in your computer science lesson is a quiz. You're a bit screwed. That's totally boring. So this is the world we live in. And so my thinking was, okay, so we've got this opportunity to get to continually engage kids. Kids want to do the drums at the same time as the bass, right? That's what they want. And the school teachers are telling me we can't teach this because we're not allowed to, really, effectively, because any time spent outside the curriculum is not as time that we won't be assessed positively for. It's time wasted. We want to be focusing on specifically on the thing which is going to be assessed, so we can get our grades higher, so we can get more funding. And so this is a problem. So this is why in Sonic Pi we don't do the loop. I don't teach the loop. Right? I've made my own loop. It's called the live loop. So you type live. It sounds way cooler. You run the code, you get an error, right? Because loops need one more thing. They need names. So this is Jane, right? She's playing the square. And this is, let's have like Fred. Fred's playing the Amen break. Okay, so they give them names. They're a bit like band members. Because in a band, what's the normal, simplest approach, right? The one-person band, where you've got a person trying to play all the instruments at once, or a separate person per style thing you're playing, a bassist and a guitarist and a singer, right? Clearly, concurrency is the simpler thing in music. So in Sonic Pi, it's also the simpler thing. So now we have concurrency. So teachers have no idea they're doing concurrency. The kids get to do what they want. Everyone's happy. They're able to tick. So we've done loops on the curriculum. All great, right? Now, this is fun. But what I've done so far, which I think is quite interesting, you probably haven't realised this, is I've been programming like you program, sort of. Okay, I haven't got types there, and I'm not running the compiler, whatever. But in general, professional programmers, which I'm sure you all are, very professional programmers, work in a very sort of timeless way, right? You have an idea, you hopefully sketch some stuff on a bit of paper, have a thought, go to the computer, type some stuff in, run the tests, run your compiler, see the results, doesn't work, go back again, right? Tear everything down, try again. Some more thoughts, some more paperwork, some more code, try it out, it's not working. You'll keep repeating until it works, git commit, done, right? That's totally fine, way of programming. But imagine doing that as a performance, right? Where if this is going, this wicked bass and drums, right? And you want to make a great, it's like, sorry, you've got to stop dancing, I'm going to change something. Right, what should I change? I think I might change this to be some octaves. I'm going to tick through those. Now, don't be worried about the parentheses in the correct position, because Lisps are awesome. Or maybe I want to actually make that a bit faster. Sorry, stop dancing again. I'm going to change it again now. Well, now it's too long, so that's going to change this release time to 0.1. Right, or that's too loud. So you can see what I'm doing. I'm doing what you would normally do. I'm having an idea, changing the code, running it, hearing it, thinking of some changes to make, tearing it down, repeating. Right, this is a normal process for programming, but it's rubbish for performance. Right, it'd be much better if I could just like comment this out, right, and it'd still be running, and maybe change the cutoff value. Right, and then maybe bring this back in. And maybe bring this back up again. Maybe change this to TV 303. Maybe use like a randomized value here. Oh, I made a mistake. What have I done wrong? Ooh. See, I made a mistake, but it's still running, right? Because I've got threads, which is great. So now I can actually start this one in sync with the existing running with Fred. It's really important to realise that you will make mistakes. And you can also switch the samples, right? So the onset thing doesn't just work with drums, it works with anything that has sort of energies that you can pick out. Now, this live loop, therefore, is not just a normal loop, is it, right? There's three things going on. There's a standard loop, which is it's repeating round. Each live loop is its own thread. I've implemented my own threading model. So although I'm using Ruby, I've built a whole ton of stuff on top, which has this sort of idempotent semantics, so that when you create a thread called thread, if there's a thread that already exists, try saying that quickly, then it doesn't create a new thread. There can only be one thread in my band, right? So, and only one Jane. And so the second time I evaluate live loop, it doesn't create a new thread, but it does modify a function called thread. So that do-end block in Ruby, it's actually one of the nicest things about Ruby. If you ever look at Ruby, there's one thing which is cool, pretty much, which is the do-end block, which is an implicit lambda that I'm passing to any method. And that really allows you to make these really nice DSLs. Like, it's not as nice as if I was writing in a Lisp, but Lisps are hard to get into schools. So, whereas this, I can say it's basically Python, and I'm in, right? So, which is basically what I do, because they ask me, why is it not Python, right? You have no chance getting Scala into schools. Good luck with that. So this do-end block is really nice because it allows me to write a block of code, which then I can change the executional context for it, right? And I can do a whole cool lot of stuff. In this case, the do-end block allows me to make that sample guitar in my E minor thing as part of a lambda, which is in the loop running in a thread, and actually it's the name of a function. And so what the thread does is it dereferences the function, gets the latest value of it, executes that, and then repeats and repeats and repeats, which means that I can actually change the body of that function with the same name. The next time the thread goes around to call it again, it sees the new behavior. And that's how I'm able to modify as it's running. And because the sleeps are not normal POSIX sleeps, these fancy sleeps I was mentioning before, then that takes care of the timing. And even though those sleeps are independent, each thread has its own notion of time, it has its own, all the state in the system is all thread local. I'm not sharing any state, even though Ruby is an object-oriented language, I'm not really using the objects in a kind of exposed way. Everything's much more functional. All the data is immutable, or I'm using numbers and immutable vectors and immutable lists. Then we're able to then independently modify and work with these different things. And this becomes really important when we get to code which is more sophisticated than this. And what do I mean by that? Well, if I have, let's think about this. One way to make a melody is to use some sort of iteration like this. And I might play note E1, that's E3 with release short like this and sleep short like time like this. Right, so I could do that, or I could actually say, let's use a scale. And scale is just is a function which returns an immutable vector of notes representing, which are that scale. So E3 minor pentatonic, say, let's tick through that. We have an arpeggiator. Tick is a method on this immutable data structure which actually increments a local thread local counter. So there's counters which are thread local, which then uses the thread local counter as an index into the vector itself. Right, so we can work with things which look like they're mutating, but they're not mutating anything except for a thread local value, which is important, and you'll see in a moment. So instead of doing tick, I can do pick. Lovely, right? So that's nice. Notice, though, it's the same every time. This is really important. So within I've got randomization, the randomization is totally deterministic. Because if this is my wicked, love it baseline or melody, I can now cut and paste this code, email it to all of you. You can paste it into your Sonic Pi and hear the same thing. Because once we start to use text as our tool for representing musical ideas, it's really important to be able to share those. And if we use randomization, then it's much harder to share that. Because I make sound that sounds, can't speak, I've been walking for last week. I might make something which sounds good for me, but I might not be able to play the game myself, and I certainly can't share it with you if it's really, truly random. Right, so we don't really care about entropy at this point. We're not doing crypto. Right, what we're doing is doing things which are, we're using randomization as a way of exploring things we can't just come up with ourselves, but also it's really important to be able to reproduce that. So, of course, we can change a random seed. Let's change random C to something else. Or great. Now, let's imagine I've got this in a loop, and I'm doing this. Right, so now I've got my repeating melody. Right? If I don't like it, I can just change this until I find something I like. Right, so I like that. That's cool. Now, I've got that going, and I've got another live loop called bar, because I can't use foo twice. And now I've got a sample bass drum house, and let's do the cutoff to be a random value between 70 and 130, and seek for half a beat. Now, if I remove this code, I'm still hearing the same melody. Now, that might make musical sense to you, but as programmers, that code might look a bit weird, because the random things, the random number generators in most languages are a global value, a global stream that I'm pulling from. And if I'm pulling rands from two separate threads, well, I have a race condition there immediately. And each thread's pulling the next rand. It's a bit like I have a single deck of cards and multiple threads are all asking for the next card from the top of the deck. And I'm just randomly giving them out to whoever's got it first, right? And depending on how my scheduler works will determine how I'm sharing those cards out. And if I have a non-determinate scheduler, which the JVM has, for example, Ruby has, then every time I run this code, I'm going to get a different interleaving of sharing the cards out. Whereas here, I could introduce this thread, which is using the randomization system, hasn't modified the original thread. So we have this idea of isolation inside the threads, so that each thread has a notion of its own randomization system. So the way I'm doing this is pretty easy, actually. It's weird. I'm not using Ruby rand, right? I wouldn't be using the JVM rand. I have loaded up an immutable vector of random values, right? A ton of them, like 44,100 of them. Actually, it's white noise as a WAV file, which I load up into memory, and then each thread has an index into that. And every time you call rand, you increment the index into that, so you get the next value of the rand. But each index is a thread local, so the threads don't interleave their calls to rand. And also, because that randomization value, the list, is a predetermined WAV file on my files as an audio file, I can implement the same randomization choices in any language. So if you like this kind of idea and you wanted to have this, you were desperate to have it in Scala, right? Oh, I need it in Scala. You could totally implement this. You'd obviously have to have slightly different syntax, of course, but the randomization system you can clone and have exactly the same randomization choices, which is really important, because if my wicked melody uses my randomization system, your randomization system will have different choices, and you won't have my wicked melody, it'd have slightly different variants. And so by having the randomization system be something that actually is portable, then we're actually free to move to other languages to consider as host languages for Sonic Pi, whilst keeping the compositions to have the same properties, which is really exciting. So the randomization system is deeply interweaved with the threading system, such that the choices are all deterministic. So that whenever you run, the goal with Sonic Pi is the same code always produces the same side effects, which means the same music, right? Regardless of race conditions. So I'm assuming I have a non-deterministic scheduler, and I'm accounting for that by doing a lot of monkey business and tricks, which is pretty fun and exciting. Right, I think I'm almost running out of time. So let me show you one more thing you can do with this do-end stuff, right, which is fun. Which is, kids will say like, "Oh, this is cool. I got a nice sound. Let's go back to this." They say, "Well, I like it to sound roomy. How do you make it like it with reverb, or make it sound like it's from a big hall?" Now, most languages that do this kind of thing, so Sonic Pi is not the only live coding language. There's a whole ton of them. They're really fun and interesting to explore. And actually, for you chaps, there's a thing called Scala Collider, which is a super collider, which is the synthesis engine I'm using here, but with the Scala language on top, which is definitely something you should definitely explore. When you're working with things like reverb, what you've got to do is you've got to actually create some kind of reverb synthesizer, and you've got to create it, which in this case we've got a local representation of that. That then has to have the right messages to create a synthesizer running on Super Collider. These synthesizers are actually quite fun. Let's have a look at one. Etc. Synth-devs. And here, graphics. So I wrote so these synthesizers are design in Clojure. They're offline compiled to this binary format. But I also wrote a graphics renderer, so you can actually see one. CD PDF. see, open Sonic Pi stereo. So this is the sampler. There we are. So there's a whole ton of stuff going on. Like these are all, this is like the audio pipeline basically to make the sampler work. So I'm showing all that because over here, the reverb will also be one of these things, right? And you have to design it, you have to instantiate it, you have to do all the plumbing inside the scenes to make sure the audio output for one thing goes in the audio input of the other thing. So I need to do that. So I need to say something like, once I've got my thing, I've got to then somehow say, I don't know, you got in Scala, you can also do that kind of stuff. Let's make some weird operator. And let's pipe it into R like this. You can do this, can't you? Yeah. As long as I can define all the types and stuff and make it all work. And so, but at this point, this is quite easy, right? But now, if I do this, I'm a bit screwed. Because I now have a resource which has been created, but it won't be garbage collected, won't be killed. So this reverb running on the synthesizer will be running forever. So I need to figure out a way to kill it. So somehow I've got to have some kind of kill or destroy or something to tie it up to free the resources. So we have kind of the same way we have with memory, right, where the garbage collector will do this work for us. We need a synthesizer collector to collect the synthesizers when they're completed. And so this kind of code makes this kind of stuff tough. So what people tend to do is tend to have like 5 reverbs available only, and you can use those, and then that's it. Right, so they'll instantiate all the stuff ahead of time, so they'll be kind of like singletons, and they can use those things, but you can only use the ones that have been allocated ahead of time. I wanted to make sure that this was 10-year-old ready. Already, we've got constructors, we've got weird operators, we've got destroyers, we've got understanding the pipelines. What happens also when you've got things in threads, like this, and then I'm putting these in threads here now, I'm like making millions of them, it's going to destroy. So you've got to really understand what's going on to be able to program this in a way that won't actually have memory leaks. So I wanted to be able to make sure this was 10-year already. So this is where the do-end block comes into play, because this do-end block is really just a way of describing a context, right? It's a lambda, right? I can say, do some stuff in here, and what I want to do with it, I want to play it with an effect, which reverb effect, and my code doesn't work, so that's a weird thing going on there. Oh, let's get this. Now I've got my iterations gone. Let's get back again. There we are. So a nice effect. So this reverb lambda will actually take care of creating the reverb synthesizer, doing all the audio pipeline stuff, and then waiting for that code inside to complete. And that might also mean not just waiting for the function to complete, but if that function spawns threads, I have to wait for those threads to complete. Right? And if they spawn other threads, I have to wait for them to complete. So now I have to watch an entire tree of threads. And also the synthesizers inside them, they can last for an arbitrary amount of time. Right? You saw before, I made a synthesizer last for 8,000 seconds. So I can't just wait for the code to complete. I can't just wait for all the threads that are created and watch them and their child threads to complete. I have to wait for all the synthesizers, all of those created to complete. So I've got a lot of callbacks here, and I'm waiting for them all to come back. So the synthesizer will tell me when a synthesizer started and when it finished. So I can then wait for all the finishes to come in, so I know I'm done, then I can kill the reverb. So this will actually take care of all of that creation and destruction for me in a way that means that when I go into schools, I don't have to think about all that stuff. So when the kid says, how do I do reverb? And obviously reverb is not on the computer science curriculum, is it? You know? So, but I can actually go and go, here you go, just write this thing at the beginning and the end. Don't tell the teacher I've told you. Right? And they're happy, it hasn't interfered with the lesson, and they made the sounds more interesting. Right? But also, this is a surprise the hell out of me, is that when I'm performing at 2 a.m. in a club in Berlin or something, and I've had a few drinks, do I want to be doing all this constructing and destructing and watching for memory leaks? No. Do you? No. Right? So this also takes care of that for me. So in a way that I can just know that I'm talking about adding reverb to this chunk of code only, and it will just take care of the creation and the destruction. In the same way that we don't want to take care too much about how our memory is being used and which objects should be freed and how and when. That makes sense. So what I'm trying to say is that there's a lot of things I'm trying to say, to be honest. One is that code, it really isn't just for business, right? It's a really, really beautiful thing that we should be using in all of our societies. And I think we should be teaching schools children in schools how to code, not to make more programmers, but to actually make a better society that has a better understanding and literacy of the world around us. And that means, I think, that we shouldn't be teaching professional programming tools, right? We should be teaching in the same way we shouldn't be teaching professional history tools, whatever they are, right? So we should be teaching kids a little bit of code, right? And finding ways to get them excited about it. Not to necessarily get them to fully understand all the bits, but just to get them not to be scared, right? Just so that we can go to a party and say we're programmers and for it to be an interesting thing, right? And for it not to be like the San Francisco, like, oh, which startup are you working for? No, what are you doing? How are you expressing yourself with the code? What things are you writing? What's interesting to you? How are you changing the world in beautiful ways? I think a much more interesting conversation to be had when you say you're a programmer. And I think we need to try and educate the world about how this could actually be a fabulous conversation. I think music is one way, only one way of doing this. It's the way I'm doing it. I'm having a lot of fun, and I recommend you have a play with it too. Certainly, if you do have that problem like me of having that conversation, when you throw out a bit of live coding, that actually can really make things much more interesting and easy to talk about. And then to get you to recognise that there is, although things can look simple, and I can use languages which perhaps you go, I don't like that language, PHP is rubbish. You can still build amazing, sophisticated things like Facebook, right? That's not in Scala. It's not in Haskell. Bits of it might be, but majority isn't, is it? And so you can build beautiful things by having good ideas and trying really hard to make them simple and understandable. Because the benefit I've found when things are simple is that the cognitive load, how much you have to think about it, reduces dramatically. And that can increase the level of your expression, it can increase the level of your fluidity, so you can come up with ideas much more in a fluid, fun, exciting way, and it can take you to more interesting places. And so there's definitely compromises to be had. Like, it's definitely worth, once you've got an idea, formalizing it, writing types, writing all the proofs, when you've got something you know what it is really well. But there are other things which you don't know what they are, and actually you don't care what they are. You're not even going to keep them, right? All these programs I've written, they've gone. I don't care. I'm not keeping them. So having ephemeral code be something that you write and you do, it will change the way you work with code. And so there are definitely things that you are, like when you use a terminal, you're writing ephemeral code. Right? And I think that ephemeral code is a really interesting, exciting place for research. And also music is a great place as well, because we've instantly got time, we've instantly got concurrency, we've instantly got a distributed program. I haven't shown you at all how I can work with other computer systems. I can work with events coming in with MIDI, so synthesizers. I can send open sound control network messages over the network and get them back again, all which feed into this time state, which actually I didn't spend much time talking about. But you can see down here this loop bar stuff. These are events coming in. I can create queues. And here we are, there's a foo queue there. I get a few of them going on. And they can be generated internally, they can be generated by external systems. They're all extremely well timed. They can take, this is like a tuple space, so I can queue 5, and 5 will get stored within a vector. And I can put arbitrary things in there like this. And so I can then go back in time and see what was the last foo, what's the next foo, and that I can pattern match over those so that I can say, wait for the next foo/star message. And that could be from another machine, that could be when I've pressed a button. And so you can really do interesting distributed programming and asynchronous programming and event-driven programming using this approach, all in a way that's just simple enough for a 10-year-old child, which I think is pretty exciting. So for me, the next stage for the Sonic Pi is actually figure out how to actually make more of this stuff much more bulletproof. So I'm really strongly considering rewriting this internal state system here in Rust, because I really want it to make it extremely well-defined, because I think everything can be built on top of that. And I think that I would really invite you to explore ways to share your programming skills with others, especially people who don't look like you, right? Who don't have the same ideas, who don't get excited in the same way you do. Find ways to share your joys with them. Right? And I think that will take you in a very interesting, different places. And I think that will broaden and it will more diversify our cultures and our communities in ways which are really, really so important right now. It's unbelievable. And I think that hopefully we'll all have a better lives. And we'll all be able to go to parties and have a nicer time. Thank you very much.